All right, so sprint number 21 reads, a teacher chooses three integers a, x, and b and writes the expression a times b on the board. On interprets the expression as a times b, while Bim interprets the expression as a times x times b. Given that On's and Bim's expressions yield the same value, compute the number of possible ordered triples a, b, x, where a, b, and x are between -10 and +10 inclusive. So first of all, if a times b is equal to a times x times b, then either x equals 1, a equals 0, b equals 0, or some combination of these things are true. So we could have both x equaling 1 and a equaling 0. We could have a and b both equaling 0. We could have b equals 0 and x equal 1, or we could have all three of these rules be satisfied. So that's a few cases, but fortunately we can simplify how we look at this. So first of all, let's think about how we could make it so that at least one of these rules is satisfied. Well, then we pick one of these three spots in a times x times b to be set as following the rule that we showed. That gives us three choices. And then for the other two, we have the choice of any integer between -10 and 10 inclusive. That's 10 negative integers, 10 positive integers, and 0. So 21 total options. So 21 choices for one of the empty spaces and 21 choices for the other empty space, giving us 3 times 21 times 21. 21 squared, you should have your squares memorized up to 30. We know that's 441, and then 441 times 3 is 1,323. And that satisfies one of our rules. Now let's say, what if it satisfies at least two of our rules? Then we're going to have three choices for the space that does not satisfy a rule. The two spaces that do satisfy a rule, they're locked in as the number that they have to be. And that third space that doesn't satisfy one of our rules can be, again, any of those numbers from -10 to +10. So it's going to be 3 times 21 options. So 63 total cases, or 63 total cases that satisfy at least two of our requirements. And of course, if it satisfies all three of our requirements, then a equals 0, b equals 0, and x equals 1. And there's only one way for us to do that. So there's one case where all three are satisfied. Now, you might think, okay, let's add up these three numbers and we'll get our ultimate answer. But you'd be incorrect, because when we found the number of cases that satisfy one rule, we only made sure that it satisfies at least one rule. We didn't make sure that it satisfies exactly one rule. So this 1,323 counts all of the times that we satisfy exactly two of the rules twice. And it also counts the times that we satisfied three of the rules too many times. So we need to subtract this number here. So if we subtract the number of times that we overcount the cases where at least two of our rules are satisfied from 1,323, then we're also going to need to add back this third case, because this case is overcounted in both our count for satisfying one of our rules and our count for satisfying two of our rules. So when we subtract 63 from 1,323, we need to add that one back. So our final answer is going to be 1,323 minus 63 plus 1. And that answer is 1,261, which is problem number D. And we're done. Thank you.
This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.